So today we're starting our next unit called stoichiometry. These first couple slides, we're not going to write a lot down. Just if it's bolded, copy it down. And then on the next couple slides coming up next, you don't have to write it down, but I do want you to mentally follow along with me. Okay. So first, we just need to know what stoichiometry is. So stoichiometry, it is just how we calculate quantities in chemical reactions. So it's how we calculate either how many reactants we need to make so much of a desired product, or it's how we can calculate how much product we should obtain based off of how many reactants we use. So why do you think it's important that we could be able to calculate either how many reactants we need or how much product we could make in a chemical reaction? How many of you bake, at home? Okay, if you're baking at home, let's say you want to bake chocolate chip cookies. Is it important to know how much ingredients you have to use to make yummy tasting chocolate chip cookies? Okay, yeah, is it important you mix all your ingredients in the correct ratios? Good, okay, same thing for chemistry, right? If we want so much of a product, is it important we know how much reactants to use? Okay. Let's also think more so chemistry in the real world. If you're a business and let's say you have to do some chemical reactions to make something, what's your number one goal if you're a business? Say that louder. To make some money. So if your ultimate goal is to make some money, is it important to be able to calculate how much product you should be making so that if you're not making as much product as you should be making, do you want to become more efficient in your process and procedures so you're not wasting money? Good, okay. You can also think of it on the flip side, let's say you need so much product made. Do you want to calculate exactly how many reactants you need, once again, so you don't waste money buying extra reactants? Good. So it's how we know exactly how many reactants we need or how many products we can make. Okay, so on this side and the next slide, you don't need to write it down, but I do want you to pay attention with me. Okay. So when we do stoichiometry, we have to look at the balanced chemical equation. So that balanced chemical equation, it just tells us the amount of reactants you have to mix and how much a product you should expect. So when we talk about quantity, we're typically going to talk about grams or moles. Okay, so for the most part, when we talk about how much reactants or how much products you need or making, we're talking grams or moles. Sometimes we'll talk liters, every now and then molecules. Okay, so take a look at this chemical reaction. So here's a balanced equation. So this is the info we can get from the balanced equation. So number one is moles. So now when we look at balanced chemical equations, I want you to think of it in terms of moles. If no coefficient is written, what number is implied right here? Okay, a 1. So for every 1 mole of nitrogen, you need to react it with 3 moles of hydrogen, and you're going to make 2 moles of ammonia. Okay, so I'm going to go through that again because this is important. So now when we look at balanced chemical equations, we look at the coefficients. And when you look at those coefficients, you need to be thinking in terms of moles. Okay. Again, if a number isn't written down, what number is implied? Okay, 1. So for every 1 mole of nitrogen, you react 3 moles of hydrogen, and you get 2 moles of ammonia. Okay. The other piece of info you can grab from a chemical reaction is just the mass of the reactants. So whatever this side weighs has to equal the mass of the products. Okay. What law is that referring to? Law of conservation of mass. Good. Okay, so take a look at this equation up here. All we're going to do is interpret it in terms of number of moles. So how many moles of H2S are here? Okay, so for every 2 moles of H2S, you have to react it with 3 moles of oxygen, and you're going to make how many moles of SO2? 2 moles of SO2, and you're going to make 2 moles of H2O. So we're going to use these coefficients. So again, whatever the coefficients are now, you're thinking of moles. Okay, so 2 moles of H2S reacts with 3 moles of oxygen. It gives you 2 moles of SO2 in 2 moles of water. Okay, so we're going to use the coefficients in the balanced equations to figure out how many moles that we'll get in a chemical reaction. So go ahead and copy this balanced equation down in your notes. Okay, so everyone should be copying this equation right now. Again, I would strongly recommend you're on paper. And then we're going to solve this example problem together. So if 0.6 moles of nitrogen react with hydrogen, how many moles of NH3 are produced? Okay, today is our foundational day for stoichiometry. So today's calculations, they're going to be relatively simple. Do you think they're going to get a little bit more complex as we go? Okay, they are. But I'm going to teach you, we're going to get some good habits of just setting things up. So you're starting with 0.6 moles of nitrogen. Usually I write that below my equation, but I just don't have space today. So by the nitrogen, I know I'm starting with 0.06 moles. And then what are you trying to solve for? If you read the word problem. Okay, NH3. So above NH3, I'm going to put a question mark. Okay, so I know that's what I'm looking for. And my unit is just going to be moles. So how many moles of NH3 could be produced? So in order to figure out this question, we're going to use something called the mole-mole ratio. And that mole-mole ratio is just the ratio of those coefficients. So if we look at nitrogen, if no coefficient is written, what number is implied? Okay, so it's a 1. I'm going to just write a note off to the side. So it's the mole-mole ratio. So nitrogen has a 1. What's the coefficient of the ammonia? 2. So you're just looking at the big number up front. Okay, so 2. So the mole-to-mole ratio of nitrogen to ammonia is a 1-to-2 ratio. Okay, so again, that's coming from here. If there's no coefficient written, what number is implied? Okay, 1. So that's where this is coming from. And then the 2 is coming from this coefficient. Okay, so we're going to set this up like dimensional analysis. I know some of you can look at that ratio and multiply in your head. However, starting Wednesday, we're going to add on where we're going to do more dimensional analysis. So to solve this problem, we're going to draw our boxes. What is the only number given in the word problem? Okay, the 0.6. So you're going to start with the only number given. And then we need to have a really good unit. So it's 0.6 moles, and it's of nitrogen. So this time, make sure you have the 0.6 moles and nitrogen, because eventually we're going to switch it to ammonia. Okay, so just 0.6 moles isn't good enough anymore. So it needs to be 0.6 moles of nitrogen. Okay, does this setup look familiar? Okay, so now we need to get from nitrogen to ammonia. Okay, so the way we do that is we use this mole-to-mole ratio, which is a 1-to-2 ratio. Okay. If moles of nitrogen is in this top box, what unit has to go in the bottom box? Okay, it has to be moles of nitrogen. You grab the number of moles based off the coefficient. And if no coefficient is written, what number is implied? Okay, so then for every 1 mole of nitrogen, you get how many moles of ammonia? Okay, so then 2 moles of ammonia. Okay, so if you look, moles of nitrogen cancel. So then the only unit that doesn't cancel is this moles of ammonia. And does that match what we want our final answer in? Okay, so then it's just time to calculate. What is 0.6 times 2? Okay, so 1.2 moles of ammonia. Okay, this time we're going to calculate the number of moles of nitrogen and hydrogen that are required to make 7.24 moles of ammonia. So you already wrote this equation down in the previous one, so you can use it again. If you want to rewrite it, you can rewrite it. Okay. We're going to calculate the number of moles of nitrogen. So I just like to put like a question mark there. We're also going to figure out the number of moles of hydrogen that you need, bless you, to make 7.24 moles of ammonia. Okay, so for this one, do you see how we're solving for two different things? Like I have 2 question marks. Okay, that's 2 different calculations. So we don't do 2 unknowns in the same equation. So 2 unknowns, 2 equations. I'm going to start with nitrogen because it's first. Okay. So to figure it out, we're going to do our dimensional analysis. What is the only number given in the word problem? Okay, so that's where you're going to start. So 7.24, and then make sure you have a good unit this time. So it's moles, and it's ammonia. I'm going to write NH3 because it's easier to write the formula than the word. Okay, and I'm going to just start with nitrogen since it's the first one. So I need to get from ammonia to nitrogen. So what do you use to go from here to here in the equation? You have to use the mole to mole ratio. Okay, so everyone say mole to mole ratio. Okay, so that's how you go from one place to another place in the equation. So how many ammonias do you have? 2. If ammonia's up here, what has to go down here? Okay. So then there's 2 moles of ammonia. And we're converting it to nitrogen. If no number is written, what number is implied? Okay. So makes 1 mole of nitrogen. Okay, so moles of ammonia cancel. The only unit that doesn't is the moles of nitrogen. So now we're just going to divide. So what's 7.24 divided by 2? $3.62. Do y'all agree? Good. Okay, and what's your unit? Moles of nitrogen. Okay, are we all the way done or just half done? Okay, just half done. We had that second question mark up there. So now we're going to solve the second part of the equation. So we're going to figure out how much hydrogen's needed to make the 7.24 moles of ammonia. Okay. Again, a different unknown, so we're going to do a different calculation. Okay. We're still starting with the only number given in the word problem. Okay, so what's the only number given? Okay, so we're still starting with 7.24 moles of ammonia. This time we need to get from ammonia to hydrogen. So what do you have to use to move from ammonia to hydrogen? What do we call that? Okay, everyone say mole to mole ratio.
Mole to mole ratio.
Good. Okay, how many moles of ammonia are there? 2. If ammonia is up here, what has to go down here? Okay, so for every 2 moles of ammonia, how many moles of hydrogen do you have to use? Okay, 3. And you just grab that from the coefficient. Okay, so moles of ammonia cancel. The only thing that doesn't cancel is this moles of hydrogen. So to calculate this, I would go 7.24 times 3. Okay. Click like equals in your calculator, get an answer, and then divide that by 2. $10.86. Do y'all agree? Okay. We haven't talked sig figs yet. The nice thing about stoichiometry, typically however many sig figs you start with is how many your answer should have. So how many are in 7.24? 3. So how many should your answer have? So what are you going to round that to? Okay, so 10.9. And what's your unit?
Moles of hydrogen.
Good. Moles of hydrogen. Okay, here we're switching gears to a new equation. So go ahead and copy down this balanced equation. So 4 aluminums plus 3 oxygens yields 2 aluminum oxides. Okay, so copy down that balanced equation. Okay, so this time we're going to figure out how many moles of aluminum are needed to form 3.7 moles of aluminum oxide. Okay, so we're looking for moles of aluminum. So I'm just going to put like my little question mark in moles under aluminum. And then we know we're trying to make 3.7 moles of aluminum oxide. Okay, so we're drawing our boxes. What number are you going to start with? That's a terrible future box. Okay, what's the only number given in the word problem? Okay, so you're starting with 3.7. What should your unit be? Okay, moles of aluminum oxide. Is the unit kind of obnoxious this time? It is. It's okay. We need it because you need it to be organized to know like which is going on top or bottom in the next boxes. Okay, so start this unit fresh. Like make sure you're starting good habits on your units. Okay, and then we're trying to get to aluminum. So how do you get from aluminum oxide to aluminum? What do you have to use? Everyone tell me, say it out loud.
Mole ratio.
Okay, so how many moles of aluminum oxide do you produce? 2, and how many moles of aluminum do you have to use? Okay, so it's a 2 to 4 ratio. If aluminum oxide is in the top box, then you have to have 2 moles of Al2O3 on the bottom. And then 4 moles of aluminum on top. Can that 2 to 4 ratio be simplified? Okay, if you are good with numbers and you can easily reduce this to like a 1 to 2 ratio, go for it. But if you're like, so-so on numbers, don't reduce, because if you're like just so-so on numbers, do you have this chance that you might reduce it wrong? Yeah. Okay. So just like some of you are fantastic and you're great at this, go for it. But if you're just like so-so, just write it exactly how it is up here. All right, so then let's calculate what's 3.7 times 4. Get an answer and then divide that by 2. 7 something?
Yeah,
7.4. What's your unit?
Moles of aluminum.
Okay, so it's moles of aluminum. All right, so this one, it's the same reaction. This time you're figuring out how many moles of oxygen are required to react completely with aluminum. So you have 14.8 moles of aluminum. This time you're figuring out how many moles of oxygen are needed. Okay, so I want you to try this one on your own. So how far can you get without my help? So I'm going to walk around. So if you need my help, call me over, and then we'll check answers. Okay, what number did you start with? Okay, so you should start with the 14.8 moles of aluminum. Okay, and then take a look up here. Okay, look up here. So you're starting with aluminum. We want to know how much oxygen you have to react with it. So how do you get from aluminum to oxygen? What do you have to use? Say it out loud. What do you have to use? Okay, you have to use that mole to mole ratio. The ratio is 4 to 3. Okay. So if aluminum is on top, what number has to go down here? Okay, and how many aluminums? 4. Okay, so 4 moles of aluminum. And then what goes on top? Okay, so 3 moles of oxygen go on top. So the aluminums cancel. You're just left with the oxygens. Okay. So before we calculate for this problem, do you even have to do anything with this side of the equation? Okay, nope. Okay, multiply the top row. So 14.8 times 3, and then divide by 4. What are you getting for a final answer? 11.1. What's your unit?
Moles of oxygen.
Okay. Moles of oxygen. Good. Try one more on your own. So it's the same equation, okay, same balanced equation. This time, calculate the number of moles of aluminum oxide formed when 0.78 moles of oxygen react with aluminum. So again, take your time to get it set up. So what number is given to you?
0.78 moles.
Okay, so you know you have 0.78 moles of oxygen. What are you trying to solve for? Okay, the aluminum oxide. So I'm going to put a question mark under aluminum oxide in moles. Okay, so you need to get from oxygen to aluminum oxide. So you try it on your own, and then we'll check answers.
Thank you.
Okay, what number are you going to start with? Okay, you're going to start with what's given to you. So you're starting with the 0.78 moles of oxygen. And then we're going from oxygen to aluminum oxide. Everyone tell me, what do you have to use to go from oxygen to aluminum oxide? Okay, mole to mole ratio. If oxygen is up here, what has to go down here? Okay, and how many moles? 3. So there's 3 moles of oxygen. And how many moles of aluminum oxide? Okay, when you calculate, what are you getting for your final answer?
0.52.
Okay, 0.52 moles Al2O3. Good.